This video is going to introduce gases, and it will conclude with the description of the various gas laws, including the ideal gas law. We're going to start with the concept of pressure. Gases exert pressure when they are enclosed in containers. And so the reason for that is because the gas particles, which you see as these red spheres, they collide with the walls of the container, and those collisions result in forces that lead to the pressure that we can measure. There are a lot of different units of pressure. We're going to use lots of these in class, and we will interconvert between different units of pressure. The first one listed here is a Pascal. That is the SI unit of pressure. We're going to talk a little bit more about that one in just a minute. We will often use millimeters of mercury, and we're going to talk about millimeters of mercury in a few minutes. A bar is a unit of pressure that represents, it's related to Pascal. So 1 Pascal is 100,000 bar. And we'll talk briefly about that, but not a lot. 1 atmosphere is very close to 1 bar. It's 1.01325 atmospheres in 1 bar. And we're going to talk about where the atmosphere unit itself comes from. And then finally, a torr is actually the same thing as a millimeter of mercury. It just has a different name. And we'll talk about that one too in a few minutes. But just so you know, there are a lot of different units of pressure, and they're all very commonly used. Now, the SI unit of pressure is a Pascal. And this picture is meant to represent the Earth. It's trying to show you that atmospheric pressure is the result of a large column of air. If you take a 1 square meter area at sea level and you go straight up through the Earth's atmosphere, then all of the air in that column has a weight, a mass that pushes down. And because of gravity, right, gravitational force, acceleration due to gravity, that exerts a force on the Earth. And so this results in what we would call atmospheric pressure. And so you can see on the right-hand side that a pressure is defined as force per unit area. And so a Pascal, which is the SI unit pressure, if you break it down into its somewhat more fundamental units, then it would be 1 Newton, which is a unit of force, divided by 1 square meter, which is a pressure. So 1 Pascal is 1 Newton per square meter. And that helps you sort of see that it's the force divided by the area. Now, if we look at the picture on the left, you can see that the mass of that column of air is 10,300 kilograms. And we can use the equation on the left. Force is mass times acceleration. That comes from physics, which you've probably taken in your lifetime. Force is mass times acceleration. So we take the mass of that column of air, we multiply by acceleration due to gravity, which is 9.8 meters per second squared. And then we end up getting about 101,000 kilogram meter per second squared. That's the same thing as about 101,000 newtons. Now, if we take that force and we divide it by 1 square meter, we end up getting that the pressure is about 101,000 Pascal. That is equivalent to the unit 1 atmosphere. And so atmospheres were defined based on our sort of standard kind of atmospheric pressure. Now, not to say that atmospheric pressure is always 1 atmosphere, because it's not. The pressure of the atmosphere will vary depending on the weather conditions, and you've probably noticed that, right? In the news, they often give you the, on the weather, they often tell you the atmospheric pressure outside. And they talk about low pressure and high pressure and things like that, because the pressure has a pretty dramatic effect on the weather. You can measure the pressure of the atmosphere using a barometer. We have a barometer in the lab that I can show you how it works. Now, if we move on, pressure, barometers work in a similar way as this sort of very simplistic diagram here, where we have mercury in a dish and it's open to the atmosphere, and then we have a tube that is sort of evacuated, and then you put it upside down inside this dish. And what happens is the atmospheric pressure, the pressure due to the atmosphere, that those gases will push down on the open part of the dish, and it will force the mercury up into that tube. Now, it will go up a certain height, and at sort of 1 atmosphere of atmospheric pressure, it will go up to a height of 760 millimeters or 76 centimeters. And that is the reason that's the sort of that's the creation, the reasoning behind the unit millimeters of mercury. So millimeters of mercury really comes from literally measuring the height of a column of mercury in millimeters, and 1 atmosphere is the equivalent of 760 millimeters of mercury. And remember that 1 torr is the same as 1 millimeter of mercury, so 1 atmosphere is also 760 torr. Now, we can also use mercury to measure the pressure of an enclosed gas. This is called an open tube manometer. And so there's a gas that's sort of green in color in this picture, and then there is a U-shaped tube that leaves that gas flask, and there is a liquid, which is mercury, inside the U part of that tube. And then the right-hand side of the tube is open to the atmosphere. That's why it's called an open tube manometer. So because it's open to the atmosphere, what happens is the atmospheric pressure, which I've abbreviated P subscript ATM, that's the atmospheric pressure, it's going to push down on that open end, and that's going to influence the height of that column of mercury. And then there's a gas enclosed in the flask as well, and if we open that stopcock like you see there, the gas will travel into the tube, and the pressure of the gas, which I've abbreviated P sub gas, pushes down on the closed end that you see, the green arrow. And so the red arrow and the green arrow will sort of push down. And depending on which one pushes down more, that will influence the height of the difference in height, or the heights of those 2 mercury columns. So when they are equal in height, then you know that the gas inside the tube is equal to atmospheric pressure. And we're going to talk about when they're different. So when you have a difference, like you do here, if that tube, the U part of that tube, is filled with mercury, then the difference in height that I've abbreviated delta H, that difference in height in millimeters will be the difference in pressure between the gas and the atmosphere in millimeters of mercury. So if you know the atmospheric pressure, then you can determine the pressure of the gas inside the tube just using the difference in the 2 heights. So let's just make sure this makes sense to everybody. On the left, we have the atmospheric pressure is equal to exactly 1 atmosphere. And on the right, the same thing, but on the left you see that the gas, the column of mercury in the tube, is higher on the left than it is on the right. So what that means is that the pressure of the gas is not pushing down. That green arrow is not going to be as large as the red arrow. So the atmosphere pushes down more, and so what that means is that the pressure of the gas is definitely less than the pressure of the atmosphere. And you would take the atmospheric pressure, which is 1 atmosphere, and you would measure the difference in height in millimeters of mercury. You would have to convert them into the same unit, but you would just subtract the 2, and that would be the pressure of the gas inside the flask. On the right-hand side, you can definitively say that the pressure of the gas is greater than the pressure of the atmosphere because it's pushing down more, and the left-hand column is lower than the right-hand column of mercury. We're going to do some practice problems with these in a few minutes. Now, let's switch gears a little bit and talk about Dalton's law of partial pressures. So this refers to when you have a mixture of 2 gases, like you see on the left. There's a mixture of 2 different gases. One gas is shown in, with red spheres, and the other gas is shown with blue spheres. Dalton's law of partial pressures states that the total pressure of a mixture of gases is the sum of the partial pressures of the individual gases that make up the mixture. Mathematically, you would write it like this, where P sub total, that's the total pressure, equals the partial pressure of A plus the partial pressure of B plus the partial pressure of C, and so on and so forth until you've gotten all the components of the mixture. The picture you see here is just 2 gases, gas A and gas B. And so the partial pressure of A is the pressure that only gas A exerts in the container. And the partial pressure of gas B is the pressure that only B exerts inside the container. So they've tried to show you that in a sort of cartoony way by showing you the same flask, but they've deleted all of the blue spheres in that middle picture to show you that whatever the pressure is that A would exert if it were by itself, that is the partial pressure of A. And so you can see that the partial pressure of A is about 1 atmosphere, and on the little gauge at the top of that flask, and the partial pressure of B is about 3 atmospheres that you can see on the gauge, and that means that the total pressure is just 1 plus 3, which gives you 4 atmospheres. We're going to use the law of partial pressures later quite a bit because it relates to a few other laws. Now, we're going to switch gears a little and talk about the different gas laws, and this would relate to one of your labs. So we're going to start with pressure and volume, and so we're going to vary one of these and then measure the effect it has on the other. Okay. So what we know, this is Boyle's law, is that what you see on the left is a volume of 1 liter and a pressure of 1 atmosphere. If we compress this and push the volume down to be half as big, so we squeeze it down into half a liter, then the pressure will be twice as large, the pressure inside. Now there are 2 ways to think about it. What they're showing you here is we're pushing down, we're increasing the pressure on the container. So we're exerting a pressure of 2 atmospheres instead of 1 atmosphere, and then we're going to measure the effect on the volume. And here it's going to push that 1 liter into half a liter. Another way to think about it is that if we reduce the volume from 1 liter to half a liter, the pressure inside that container will double. So there are 2 ways to think about it depending on which one you're changing and then which one you're measuring the effect on. But either way, it works the same way. If you double the pressure, the volume will be half as big. And so what that means is if we take these values, so the values in table 9.2 would be if you exerted certain pressures and then you measure the effect on the volume, then that would be plotted on the right. And so pressure is the x variable, that is the independent variable, the one that you change to see the effect on what's on y. And then the dependent variable depends on x. Now you could have done it the other way, it doesn't really matter, take the same gas, put it in a smaller container and measure the effect on the pressure. That would give you the same shaped curve. And so here what you get is a hyperbolic curve. And I show that, that's shown here on the left, but if instead we plot volume versus the inverse of pressure, volume versus 1 over p, then what you get is a linear graph. And so both of these graphs, either one by itself or both together, tell us that pressure and volume are inversely proportional to each other. That means that if one of them goes up, the other one goes down. And you can even be more specific. You could say if one of them doubles, the other one is half as big. If one of them is tripled, the other one is a third as big. If one of them is multiplied by 10, the other one is divided by 10. Now let's talk about temperature and volume. So here, if we take our gas that has a certain pressure, and it's in a half-liter container. If we heat it up, what's going to happen is those gas particles are going to move around and they're going to push out on the container and they're going to expand and occupy a larger volume. So you can see the temperature goes from 200 Kelvin to 400 Kelvin. It's kind of important that you know that temperatures for gas laws and for all of these equations to work properly, the temperature has to be an absolute temperature. It has to be in the Kelvin scale. So whenever you're dealing with temperature, you've got to convert from Celsius to Kelvin. So here we double the Kelvin temperature, or the absolute temperature, and that has the effect of doubling the volume. Okay, so what we can say is that temperature and volume are directly proportional to each other. When one goes up, the other goes up, and they go up, they're directly proportional, which means if one is doubled, the other is doubled. If one is tripled, the other is tripled. If one is multiplied by 10, the other is multiplied by 10, etc. We can plot this volume. So temperature here is our independent variable. That's what we're varying. And then volume is the dependent variable that we measure. But you could have done it the other way and you would still get the same linear graph. And so this says that volume and temperature are directly proportional to each other. Now what you notice here is that if we plot this in degrees Celsius, then the value where the volume reaches 0, you'll notice, right? So where y is 0, that temperature is about, it looks like it's close to negative 300. So if we instead plot this, and that value where the volume is going to reach zero represents absolute zero. That's the minimum possible temperature that you can have. Was Charles's law, the relationship between volume and temperature being directly proportional. The last one is called Avogadro's law, and this is the relationship between volume and how many moles of gas you have. And so on the left-hand side, if we have a mole of gas enclosed in this container at 1 atmosphere pressure and a certain constant temperature, if we double the number of moles and we do some sort of reaction, or we add more moles to make it twice as much, go from 1 to 2, then that is going to double the volume of the container because more gas occupies more space. And so volume and moles of gas are directly proportional to each other. Now this is just one more graph I want, and one more sort of image I wanted to show you, and this just shows you that the molar volume of an ideal gas, what that means is the volume that 1 mole will occupy, and this is going to be at standard temperature and pressure, STP. So for gas laws, standard temperature and pressure is 0 degrees Celsius and 1 atmosphere of pressure. So at that temperature and pressure, 1 mole of any gas behaving ideally will occupy a volume of 22.4 liters. Now in class we have this little beach ball that I'll probably bring, or would have shown you, that represents that volume, and it's always much smaller than you think it's going to be, but it's about a beach ball size. It's not very big, but 22.4 liters. So that's sort of the standard volume of 1 mole of gas at STP. Now let's review these gas laws, and we're going to put them together. So Boyle's law, Charles's law, and Avogadro's law are shown here graphically. So if we think about Boyle's law, that states that pressure and volume are inversely proportional to each other. So what that what that means is that pressure times volume is a constant. And so if you look at that equation, that means that if pressure is doubled, then the volume must go down twofold in order to stay the same constant on the right-hand side, right? So if we have a pressure times a volume and it equals a constant, that means, and that's assuming everything stays constant, right? You're keeping a constant number of moles of gas and a constant temperature. Then if one goes up by 10 times, the other one has to go down 10 times. Otherwise, when you multiply them together, you don't get a constant. So pressure times volume is a constant. That's another way of stating Boyle's law. That's another way of saying mathematically that pressure and volume are inversely proportional to each other. Now Charles's law, volume and temperature are directly proportional to each other, which means that volume is equal to temperature times some constant. That's another way of saying that they are directly proportional. And the last one, we can write a similar expression, volume to a constant times N, which is moles of gas. So if we put all these equations together, we have the 4 possible variables: pressure, volume, temperature, and moles of gas. Pressure and volume need to be on the same side of the equation like you see them here because they are inversely proportional to each other. Temperature and moles of gas need to be on the opposite side of the equation as volume. Okay, so when we put these together, we end up getting that pressure and volume on the left, multiply them together, equals N times T, and there's another constant that we have in there, which is capital R. That's the ideal gas constant. PV equals nRT. If you took any kind of chemistry in high school, you certainly would have learned the ideal gas law, and we will use the ideal gas law, and we will use it not only to just plug in numbers and see what we get for the one unknown value, but we will also use it to see how, if the volume doubles, what happens to the pressure, things like that. So we'll do some practice problems at the end. So this is one set of practice problems. There's quite a few here. So this will either be the same part of this video, or I might make it a separate video. So we're going to go through each of these problems that relates to gas laws. First, we're going to start with a sample of gas at initial pressure 295 torr occupies a certain volume. If the gas is compressed to a smaller volume, what will the new pressure be? So in this case, we have 2 different volumes and 2 different pressures, but the temperature is constant, and it lists a sample of gas, which means that the moles are constant as well. So if this is the ideal gas law, if we put everything that changes on one side, and we put everything that stays constant on the other side, like we have here, then we can say that P times V is a constant, which means we can write that P1 times V1 equals P2 times V2. So if we change pressure, the volume must change accordingly so that when you multiply them together, you still get the same value, right? So if the pressure doubles, the volume should be half as big. If the volume doubles, the pressure will be half as big. So they are inversely related to each other. We use this equation. We're going to plug the numbers in that we have. So P1 is 295. P2 is what we're solving for. We're just going to plug in values, and we solve that P2 is equal to 510.96226. Looks like everything has 3 significant figures, so we need to round that to 511. It's going to have the same units as the original pressure, which is torr. Number 2, we have a sample of gas in a fixed volume container. That implies that the volume is constant. We have a temperature given and then a second temperature given, so the temperature changes, and the question is, how does the pressure change correspondingly with that temperature change? So here P and T change, but everything else stays the same, because this also says a sample of gas, which implies that the sample isn't changing, it's just some gas in a container. So N is constant, V is constant. So now we have, if we label things that change and things that stay constant, we need to move everything that changes to one side of the equation so we can write our equation for what we're going to use here. So if we algebraically manipulate this equation so that everything that changes is on the left and everything that stays constant is on the right, then that means P divided by T equals a constant, which means we can write a new expression, which is P1 over T1 equals P2 over T2. And we're going to use this expression, and we're going to plug numbers in. Now these are the numbers from the problem. We're going to solve for P2. One thing you have to remember is that temperature, on any time you're using gas law equations, you have to convert the temperature into Kelvin. You cannot use Celsius temperature, and you certainly can't use Fahrenheit temperature. So you have to convert everything into Kelvin. Now you can keep pressures as torr or millimeters of mercury or atmospheres, whatever it's in. It doesn't have to be in a specific unit. The temperature is the only one that's very specific. It has to be in Kelvin. Now if you plug these in, you solve for P2. You get that P2 equals 564 torr. Has 3 sig figs, like the original number, same units. And one thing you can also verify is that the temperature increased, which means the pressure should increase, right? They are directly proportional to each other based on the lab you did, based on the other things we've talked about in class. So if the temperature increases, the pressure should also increase, which it does, so that's good. Check. Number 3, we have ozone being converted into molecular oxygen. The ozone is trapped in a 1-liter container. That means that the volume is constant, it does not change. It has 1 atmosphere pressure initially, but if you convert all of the ozone into oxygen, the pressure will change because moles of gas changes. So now if we think about what mathematical expression we're going to use for that, we're changing N from 2 to 3, and we're changing pressure. So now if we look at our PV equals nRT equation, this is just saying it's in the same container. Volume is constant. So now if we label things that are constant versus things that change, pressure and N will change. So if we move those algebraically to be on the same side of the equation, that means P divided by N is a constant, which means our new mathematical expression is P1 over N1 equals P2 over N2. Now if we plug in numbers here, we have 1 atmosphere pressure in the numerator on the left. We're solving for the numerator on the right. We have 2 moles of gas on the left and 3 moles of gas in the denominator on the right. So we're going to solve for P2, and you get that P2 is 1.5 atmospheres with 2 sig figs, because the original number given was 1.0, which has 2 sig figs. Now we're going to move on to number 4. We have a sample of gas with a mass of 10 grams occupies a volume of 34.3 5 liters at a temperature of 206 Kelvin and a pressure of 3.92 atmospheres. What is its molar mass? So here we just need to use the ideal gas law. So we know V, and we know T, and we know P. So based on the ideal gas law, we should be able to solve for N, which is the only variable. R is on our table here. I'm going to plug that in. That's from your equation sheet. Solve for N. Atmospheres cancels, Kelvin cancels, liters cancel, and you end up with moles. So N is 7.996405, etc. moles. Molecular weight, or molar mass, is mass divided by moles, and so we have a 10-gram sample. We know that that 10-gram sample matches this number of moles, and so we're going to say that the 10 grams and the 7.9964 moles are the same sample. So you do 10 grams divided by 7.9964 moles, and you get 1.25 grams per mole. Obviously didn't think about that molecular weight very much because that doesn't match any gas that I've ever heard of. Number 5, the decomposition of potassium perchlorate yields potassium chloride and oxygen gas. If 12 grams of potassium perchlorate decompose at 298 Kelvin and 1 atmosphere pressure, what volume of gas will be created? So here we're using the ideal gas law, and we're using some stoichiometry. We have to figure out how many moles of oxygen are created. So we start with 12 grams of potassium perchlorate, and we convert that into moles of oxygen that form. So we're going to start with the reaction that occurs between the potassium perchlorate decomposes into KCl and oxygen. We're going to calculate the molecular weight of KCl, potassium perchlorate. So 39.10 plus chlorine is 35.45 plus 4 times 16 gives you 138.55 grams per mole. So we're going to divide 12 grams by the molecular weight to get moles of potassium perchlorate. That's the reactant. We're going to convert that into moles of oxygen using the stoichiometry from the equation. 1 mole of potassium perchlorate will form 2 moles of oxygen. And that gives me 0.17322 moles of oxygen. We're going to use that in the ideal gas law, along with the other values we're given in the equation. And we're going to solve for V. So in this case, volume, you plug all the numbers in, and you end up getting 4.23803 liters. We're going to round that to 4 liters. That just has one significant figure because the pressure was given with just 1 sig fig. I probably should have thought twice about that, but I didn't. Now, number 6, consider the apparatus shown to the right. Assuming the temperature does not change, what will be the resulting pressure inside the apparatus if both stopcocks are opened? So this is a problem that relates to partial pressures. So what we're going to do is we're going to allow them to mix together. We all know if we open the stopcocks, they'll all mix together, and all 3 gases will occupy a larger volume than they do now. So if we take, this is definitely a application of the law of partial pressures, where the overall total pressure will be equal to the sum of the individual partial pressures. And that equation is shown up here at the top. So P total will equal the partial pressure of CO2 plus the partial pressure of hydrogen plus the partial pressure of argon. However, once we mix these together, the partial pressures are going to change, because over here you see, if we just take CO2 for example, CO2, before we mix it, before we allow it to expand into the entire container, it only occupies a volume of 1.50 liters. But once we open both stopcocks, it will be allowed to occupy the entire volume, which would be 1.5 plus 1 plus 2, which would be 4.5 liters. And so we have to calculate the new partial pressure once each gas is allowed to expand into the entire container. You can't just simply add them up. So we'll start with CO2. So once we allow the CO2 to sort of expand, like you see here, now CO2 is going to occupy the entire container. So if we want to calculate just the partial pressure of CO2 when we are ignoring argon and hydrogen, then our new pressure is just going to be P1 V1 equals P2 V2. So we plug in the original pressure, 2.13 atmospheres, times 1.5 liters, and then we're going to divide that by 4.5. 4.5 liters is the overall new volume at the end, and you solve for P2, and you get 0.71 atmospheres. We do the same thing for hydrogen. We calculate the new P2, and that's 0.1913 atmospheres. We plug that in. And argon, if we allow that to expand, we get a new P2 of 0.5111 forever atmospheres. And now we're going to add them all together and figure out the overall partial pressure when we think about all of them in there together is the sum. And so we just add them up, and P total equals 0.511 plus 1.41244. Oh, sorry, 0.71 plus 0.1913 plus 0.5111 gives me 1.412, which rounds to 1.41 atmospheres. So that's the total pressure once we've added each of the individual partial pressures, and those we calculated in red and blue and gray at the bottom there, right? The pressure changes. The pressure should go down because you're each allowed to occupy a larger container. Now we're going to do one more set of problems. We have oxygen that we're preparing by heating mercury 2 oxide. What volume in liters of oxygen is created at standard temperature and pressure by heating 10.57 grams of mercury oxide? So let's start by talking about STP. We'll do that in a second. 10.57 grams of mercury oxide. Mercury is here. Oxygen is here. We're going to convert grams to moles. Grams cancel. Now, the mole ratio is 2 to 1. So 1 mole of oxygen will form for every 2 moles of mercury oxide. So we have moles of oxygen here. That's going to be in our ideal gas law. Now STP, in addition to being a band from the 90s, is for gas laws, STP is 0 degrees Celsius or 273.15 Kelvin, and the pressure is 1 atmosphere. So when we plug in these values, you're going to solve for V. The volume is 0.54718. That's going to be liters because everything else is going to cancel out here. And you're going to round to 3 sig figs. And that's because STP, these are going to be exact numbers because it's STP. So you're going to be limited actually by your value for R, which is kind of unusual. But the equation sheet only has 3 sig figs for R. If R had been given to a lot more sig figs, then you would be limited to 4 sig figs because 10.57 grams was the mass that was given. That's probably the preferable limiting factor, but it's not in this case. Number 2, calculate the density in grams per liter of methane gas, CH4, at STP, assuming it behaves ideally. So that implies to you that you should be using the ideal gas law to answer this question. Now we're looking for grams per liter, and there are a few things we know about this. STP means 0 degrees Celsius, 273 Kelvin, and 1 atmosphere pressure. We also know that PV equals nRT. We also know the value for R. We also know that this is methane gas, which means we see the formula, which means we can also calculate the molar mass, grams per mole. And you can see that we're looking for density in grams per liter, and then moles is related to the ideal gas law. So somehow that grams per mole is going to matter. So we know we need the ideal gas law. So there's 2 ways to do these problems. One is you can use the information given to calculate the volume of 1 mole of methane at standard temperature and pressure. And generally, any gas that behaves ideally is going to occupy a volume of 22.4 liters at standard temperature and pressure. You can plug those numbers in and get, so that's the volume. So the density in grams per liter, because you know the mass of the same sample, which is 1 mole, will have a mass of the molecular weight, 16.042 grams. So you know that 1 mole at STP, if it behaves ideally, should occupy the volume of 22.4 liters. Now you can calculate this by plugging these numbers in here. You plug in a 1 for N, you plug in, because it's 1 mole, and you plug in the ideal gas constant here from your equation sheet. STP says that this is 273.15 Kelvin and the pressure is 1 atmosphere. That should give you a number that's pretty close to 22.4. Then you know that that is the volume of 1 mole, and you know the mass of 1 mole is 16. So you just take 16 and divide by 22.4, and that should give you 0.71616 or 0.7162 grams per liter. The other way to do this problem, which a lot of people prefer, is to just use all the information you're given and combine it in some voodoo magic way that allows the units to cancel until you get grams over liters. Okay, so I know that seems kind of weird and mysterious, but you have a lot of parameters that you can put together to get grams on the top and liters on the bottom. Okay, I'm assuming you guys are pretty good at doing this. So let's think about the things we know. We know the molecular weight is grams per mole, and we know that grams need to be ultimately on the top. So if we put the molecular weight like this, where grams are on the top and 1 mole is on the bottom, I'm going to put that there. Now, if we think about the other things we know the ideal gas constant is liter atmospheres per mole Kelvin. So that means that if we combine that in here, moles has to be on the top because you want it to cancel with moles on the bottom here. Because ultimately you want all of this mumbo jumbo to have grams on the top and liters on the bottom and nothing else. So everything else has to cancel. So we have grams on the top. Moles is going to cancel with moles down here. We have Kelvin on the top. We need to get rid of that. We have liters on the bottom. That's good, but we also have atmospheres down here. So we have to get rid of Kelvin and atmospheres before we're all the way done. So the Kelvin, the temperature, that means the temperature needs to go near here. I'm just showing you that I've got units so far. 1 atmosphere pressure goes on the top to cancel, and the Kelvin temperature has to go on the bottom so that it cancels with Kelvin on the top. So now when you plug all that in, you have grams per liter, and everything else cancels out, and you end up with 0.7153 grams per liter. .715. Sorry, I'm limited by my ideal gas constant. Number 3, determine the molar mass. That's grams per mole of an ideal gas. We need the ideal gas law. It has the density, temperature, and pressure here. So again, 2 ways. It's the same exact thing. We're just looking for something else. We're looking for grams per mole instead. So method 2 says to combine values and cancel units until you get grams over moles. So we're going to start with the density that was given. I'm putting it this way because I want grams on the top, just like it is here. We need to cancel that liter, which means I'm going to use the ideal gas constant again, but this time it's going to be on the top because I want liters up here to cancel with liters down here, and I want moles in the denominator because I want moles in the denominator of my answer. Now if we look at what's left, we've got grams on the top and moles on the bottom. Liters cancels, but I have to get rid of the atmospheres and the Kelvin. So that means I put 298.15 Kelvin on the top, and I have to convert my millimeters of mercury into atmospheres, 0.98947. And I'm going to end up moving that to be on the bottom, 1 over atmospheres there. And that's going to cancel down there. So that's going to give me grams per mole, and everything else should cancel, and I get 26.0 grams per mole. Or another way to do the same problem, so we already did that, that would be the answer, but if you wanted to do it a different way, you know the mass of 1 liter because that's the density. If you're given the density, then as long as you have 1 liter exactly, then you know you have 1.053 grams. If you know you can figure out the mass of 1 liter, then if all you have to do is figure out how many moles. You just need to calculate how many moles are in 1 liter, use the ideal gas law, solve for N, you know all the values, and you plug in, you get 0.0404, and you end up solving for 26.0 grams per mole. You should get the same answer. There's just 2 different ways to do the same problem. There are probably other ways too. Number 4, we have a 15-liter flask containing 10 grams of oxygen and 24 grams of helium at 315 Kelvin. Calculate the partial pressure of oxygen and the total pressure in atmospheres. So the partial pressure of oxygen, we can use the ideal gas law. We're going to convert first the mass of oxygen into moles, which means it's going to be 0.3125 moles. That means the partial pressure of oxygen is going to be equal to nRT over V. N we plug in here, temperature is 315, the volume is 15 liters, and we know R from the equation. So you get 0.539 atmospheres is the partial pressure of oxygen. The total pressure is there are 2 ways to do this. You can either calculate the partial pressure of helium and add that to the partial pressure we calculated for oxygen, or you can just go straight to the total pressure by adding up the moles, total moles, right? So we have N total times R times T divided by V. So the N total is going to be moles of oxygen plus moles of helium. Moles of oxygen we already calculated earlier, but we need to know how many moles 24 grams is. Helium has a molar mass of 4.003, it's here. So 24 grams divided by 4.003 gives you 5.9955 moles of helium. If you add that to the moles of oxygen we calculated at the beginning, you get 6.308. And then you solve for P total, and you get 10.8756, or 10.9 atmospheres total. You should get the same value regardless of how you do it. Number 5, consider the gas sample on the left and indicate the relative change in volume if the changes described are made. So this is sort of a qualitative question, but you do need some numbers in here, but you're not given a value. You're just expected to answer how the other parameter will change. So what happens to the volume, V, if the temperature, T, is increased by a factor of 1.5? So it's increased 1.5-fold at constant moles of gas and constant pressure. So volume and temperature are on opposite sides of the ideal gas law, which means they are directly proportional to each other, right? I think that was Charles's law, right? So if temperature is increased by a factor of 1.5, that means volume will also increase by a factor of 1.5. Part B, what happens to volume if N and P are both doubled at the same temperature? So T is a constant, but here volume, you have to think about it with both of these things changing. So volume is directly proportional to moles of gas because they're on opposite sides of the ideal gas law. V and P are on the same side of the ideal gas law, so that means they are inversely proportional. So if you double N, that means that the volume should double. But if you double P, that means that the volume should be half as big. So if you take both of those, so that's a divided by 2. If you take both of those together and combine the effect, that means, so times 2 and divided by 2, that means there should be no effect on volume if you do both of these things simultaneously.